So, a very good morning to all of you, and today I'm going to proceed on from the previous lecture that I demonstrated on the total magnetic moment of an atom, and probably we calculated we actually obtained an expression for the Landé spreading factor. And today we'll be talking about the same problem that we have, and we have a one electron atom, and we are subjecting this one electron atom to an external magnetic field. And in doing so, when we apply the magnetic field to this atom, the motion of the electron precesses. It precesses along the direction of the applied magnetic field. So the target of today's video is basically to basically obtain an expression for Larmour's frequency, and then we may extend this this demonstration to the selection rules. So what we have is we have an atom, and this atom has an electron, and this electron is revolving around the nucleus, and the plane of this atom is basically perpendicular to the orbital angular momentum of the electron. And what we have been doing is we have been applying a magnetic field in z direction. So what's going to happen when we are applying the magnetic field? The angular momentum, which is basically conserved, the magnitude of angular momentum is conserved, but the direction of the angular momentum keeps on changing. So it changes, and you have a precession of angular momentum. So if I choose my angular momentum here as L, and the angle between this angular momentum and the applied magnetic field is B, and assuming this angle to be equal to theta. Now, what we expect here is when we apply the magnetic field, what happens to the angular momentum? So what we have a plane, and this plane is basically the plane of velocity vector and the position vector of the orbit of an electron. And in generality, we should say that what we assume here is that the electron is revolving in a plane, and electron is in the same plane, and the nucleus of this atom is also in the same plane. Now, as we understand from the definition of the angular momentum, suppose if I assume that this is angular momentum, the angular momentum is perpendicular. It's perpendicular to the plane of velocity and position vector. The plane in which the electron is shown to be moving. So what we do, if I take this this angular momentum, say for the sake of argument, if this is my angular momentum, so this is going to be the plane of the electron in which the electron is moving, and my magnetic field is in this direction. I'm applying a magnetic field in this direction. So if I apply the magnetic field in this direction, what happens is that this angular momentum, the direction of this angular momentum keeps on changing. It changes, and at the same time, when you have the change in the direction of the angular momentum, one thing you have to keep in mind that the magnitude of the angular momentum does not change. It's conserved, it remains same. But at the same time, the plane that we have, this plane also reorients with respect to the changing direction of the orbital angular momentum. So this is my angular momentum, and the magnitude of angular momentum at some later time will be same. And if I make a projection of this and assume that this angle is d theta. So on applying the magnetic field, what we obtain is we obtain a precessional motion of the electron, and the direction of the angular momentum keeps on changing with respect to the magnetic field, but its magnitude is constant. Its magnitude does not change. And at the same time, we seek the magnetic moment of the electron, which is opposite to the orbital angular momentum. So that has to be mu L, and if I make a projection like this, and if I make a projection like this, I will have another cone in terms of the magnetic moment of this electron. So this cone is a reflection of the magnetic moment of the electron, so there is a precession along the direction of the magnetic field, and this cone is a representative of the changing orientation of angular momentum of the electron with respect to the applied magnetic field. So in moving from here, now what we are interested in is we are interested in developing the frequency, what's called as Larmour frequency. Larmour frequency. And in doing so, I can define the angular momentum as the cross product of R and momentum. And I can say that this L is R. If I write down the magnitude of angular momentum, this will be Rp sine and theta. So this is my angular momentum. And obviously, when you have an angular momentum, you have the changing angular momentum results in the torque. So you can have the torque leading to the angular momentum, and the reverse, we can say the reverse, the change in angular momentum leading to what's called as torque. So we can immediately think about the torque. So what is torque? Torque, as we know from the basic classical physics, it is rate of change of angular momentum. So torque is rate of change of angular momentum, and that torque will be perpendicular to the plane in which this electron is moving. So this torque will keep on being perpendicular to the plane in which this electron is moving, as long as the direction of the torque in this case is concerned. So we have torque equal to dL by dt. Now let's do some more geometry here. So we can predict that this is our 90-degree angle. If this is 90-degree angle, then this length is, it has to be sine. This length, in terms of this right angle triangle, you have a right angle triangle like this, and you want to measure this. Suppose this is x, this is your 90-degree angle, and this is your L, and we can immediately write down sine of theta in this triangle. You can see this triangle. In this triangle, sine of theta. Sine of theta will be perpendicular. This length is the perpendicular, so I choose that as x divided by the hypotenuse. The hypotenuse is always opposite to 90 degree, so this has to be L. So x, the length of this vector is L sine theta. So this is x. Okay. Now, if I want to calculate this, what is this? This is basically the change in angular momentum dl, and I can treat a simple, you have a situation like this in which you have an arc. This arc is of length dl, and this is already calculated as L sine theta, and the angle here that we have is d theta. So as we know that this arc is r times this angle, so what will be dl? From this dl it will be L sine theta d theta. So this is dl, and we can immediately substitute the value of this dl in the equation of torque, and we can calculate the torque. And what's torque? We understand what torque is, and so torque is, instead of dl, I'm going to write L sine theta, then d theta divided by dt. Now, this has to be dt. Now, we better understand that the time derivative of the angular displacement is nothing but angular velocity omega. So omega is the angular, call it angular velocity, or you call it angular frequency. So this is the angular velocity. So what we have here is d theta by dt. So for this d theta by dt, we can use omega, and what will be our torque? So our torque will be, it will be L sine theta omega. Now, from this equation, we can immediately calculate the frequency. And that angular frequency omega is nothing but it is torque divided by L sine theta. Now, at the same time, we understand what we have is we have an atom, and this atom is a magnet itself. It has a dipole moment, and if it has a dipole moment, when you subject a magnet in an external magnetic field, it leads to the torque, and we can write down the torque for this magnetic dipole in the form of atom. And we can write down its torque in terms of its dipole moment. And we know from the basics that the torque is the product, the cross product of orbital magnetic moment and the magnetic field that you are applying externally to this atom. So the torque is the cross product of the magnetic moment and the applied magnetic field. So if I write down the magnitude of this torque will be mu L b and sine theta. So if I call this as equation 1 and I call this as equation 2, and what I do is I substitute equation 2 in equation 1. What am I going to do is I'm going to calculate the Larmour's angular frequency. So omega, what will be omega? Omega will come out to be, for the torque I'm going to write down mu L b, then you have sine theta divided by, so what's in the denominator? In the denominator we have L sine theta. In the denominator we have L sine theta. The sine theta and sine theta will go, so omega will be mu L by L b. And from the basic definition of orbital magnetic moment of one electron atom, we know that the magnitude of mu L, if I write down only magnitude, is minus, it has to be plus because I'm talking about the magnitude. So this is E by 2m times L. So from this equation, we can see that mu L by L is nothing but E by 2m. So we can replace the ratio between the orbital magnetic moment of electron with the orbital angular momentum by a constant. And what's that constant? That's E by 2n, which is also called as gyromagnetic ratio. So omega will be E by 2n times B. And we can see from this equation that you can influence the angular frequency of the electron only by varying the magnetic field that you are applying on this electron. Because everything else is a constant. E is the charge of the electron, m is the mass of the electron, and 2 is just a number. So we can see that this omega has a proportionality with magnetic field. So you can influence the frequency of the motion of the electron by applying the external magnetic field. So it is the external magnetic field that decides that whether the frequency of this electron is going to increase or it's going to decrease. So we can write down, because omega is nothing but 2 pi mu, so we can write down 2 pi mu is E by 2n times B. So we can calculate this Larmour's frequency as, so the Larmour's frequency nu is nothing but E by 2n, 2 2s are, it will give us 4 pi n and B. So this is our Larmour frequency, and this expression certainly becomes helpful when you try to explain the normal Zeeman effect, the splitting of the spectral lines in presence of magnetic field. So this way what we have done is we have obtained the expression for the Larmour's frequency, and what basically we have seen is that how the external magnetic field that we apply to an atom having one electron in motion, leading to a precession, along the direction of the applied magnetic field. Now, at the same instant, let me extend down this. Let's talk about selection rule, because we have already gone through the problem of hydrogen atom. We have solved the problem of hydrogen atom using Schrodinger's equation, and we have obtained the set of 3 quantum numbers for hydrogen atom as the principal quantum number L, orbital quantum the principal quantum number N, the orbital quantum number L, and the magnetic quantum number NL. Now, the point of contention is that what we want to understand here is what's a selection rule. I mean, what we find is that in a hydrogen atom you have an electron, and electron is in the first orbit, and there are the other orbits which are empty, and electron has a probability when you subject this atom to an external energy, this electron can go into the excited states. Now, can it go in all excited states, or there is a restriction to move from the ground state to the excited state, or to come back from the excited state to the ground state, which basically is one of the postulates of Bohr model of atom, which says that if you have a transition from high energy level to the lower energy level, it leads to the emission of the energy. And the energy is quantized. You can have the absorption of the energy, and you can have the emission of the energy. Now the point is, so we'll be talking about selection rule here. Just to give you an idea of selection rule. Selection rule. So you cannot assume that electron will have a transition to any of the states in the hydrogen atom. No, there are restrictions, and these restrictions we define as selection rules. And what is the basis of this selection rule is, from quantum point of view, in quantum mechanics, what we calculate is the expectation value. And expectation value. And the expectation value of an operator can be calculated using an integral moving from minus infinity to plus infinity. And say you have an operator A, then you have psi, then you have psi star, and you have dx. If I take a case of one dimension, and this is our expectation value. Now, how does expectation value, the measurement of the expectation value, the calculation of the expectation value leads to something what's called as allowed transitions and forbidden transitions. So for that, what we have is, suppose we are making a transition, and this transition, we are looking for a transition taking place from, say, I calculate the expectation value and I calculate it from minus infinity to plus infinity. So this is x. I have a transition to the nth state, and this transition has to happen from n dx. Now this integral will give me the measure of the expectation value. Now if this integral gives me the measure of the expectation value, and if I obtain, on solving this integral, if I obtain the value of this integral is equal to 0, then such a kind of transition from some final state to the initial state is forbidden. So obtaining the result of this integral as equal to 0 leads to what's called as forbidden transition. Forbidden transition. So that means if you expect a transition, the transition that can take place in hydrogen atom, say for the sake of argument, the transition is only possible if I have a non-zero value of this expectation. So if I choose the expectation value, say in case of hydrogen atom, if I choose hydrogen atom, and for that I have a wave function psi n l m l, and I can choose a state psi n1 l1 m l1, and a state vector psi n2 l2 m l2. And if I calculate the expectation value of this, say from minus infinity to plus infinity, say some u and psi n1 l1 m l1 psi star n2 l2 m l2 dv, and if I get a non-zero value of this integral, this will automatically lead to an allowed transition. It will lead to the allowed transition in hydrogen atoms. So the allowed transitions that we have, they come up in the form of the selection rule, and the non-zero value of this integral is possible, and when it is possible to have a non-zero value of this integral, it needs a basic condition. The basic condition for that is that the change in orbital angular momentum. So if I represent that change as delta L, this delta L should change only by plus minus 1, and the change in magnetic quantum number, delta ML should be either 0 or it should be plus minus 1. So you can define all those transitions, you can expect all those transitions in hydrogen atom where the orbital angular momentum quantum number is changing either by +1 or it's changing by -1. At the same time, the magnetic quantum number is either the change in the magnetic quantum number is 0 or it is changing by ±1. So this is the key for demonstrating the allowed and the forbidden transitions that we have in case of hydrogen atom, and we can sketch down that as an exercise. You can sketch down all of those possibilities. So this is n equal to 1, n equal to 2, n equal to 3, n equal to 4, and you will be able to demonstrate all of those transitions. L is equal to 1 and L is equal to 2. So you can demonstrate all of those, because all of those allowed transitions, and you can also demonstrate the transitions that are not allowed by the selection rule. So such kind of transitions are not going to happen in which the delta L is not changing by ±1, in which delta ML is not changing either by 0 or ±1. All of those transitions will be treated as forbidden transitions. So we can treat them all as forbidden transitions, and all those transitions in which delta L is ±1 and delta ML is 0 ±1 leads to what's called as allowed transitions in hydrogen atoms. So with this, I would like to end this talk, and I hope you will at least get some basic idea about what we have demonstrated here.